So now we're getting to the next little topic, Newton's second law. Yeah, there are two Newton's second law. The first one you know all about. It's force equals mass times acceleration. And now here's the second one. It's torque equals moment of inertia times angular acceleration. Yeah. Or maybe this is slightly more useful. Angular acceleration is equal to the torque divided by the moment of inertia. So yeah, you see, the moment of inertia is playing the same role as mass was before. So let's have a little example. I've got a bicycle wheel, and it has a moment of inertia which happens to be 3.6 kilogram meters squared. I'm applying a force. It looks like it's a rope or something on a spool, and so it's unrolling and it's pulling this this pulley thing right here. So our radius from the axis of rotation out to here is 4 centimeters, 0.04 meters when you convert. And the force is this way. And the question is, what is the angular acceleration? All right. Now, I made the angle easy here, right? So if I extend the r vector, the angle is positive 90 degrees. So 90. So the sine of 90 degrees is just going to be 1, positive 1. So I didn't bother with that, but you could imagine that there's a sine of 90 degrees stuck right in here, which is 1. So it's 0.04 times 200 times 1, and which works out to 8 Newton meters. At least that's the magnitude of the torque. Okay, now let's use the second law. So the second law is alpha equals tau over I. So I'm leaving out the vector signs here, so I have just the magnitude of alpha is equal to the magnitude of the torque divided by the moment of inertia. So it's 8 from here divided by 3.6, which was a given, and I get 2.22 radians per second squared, and in the positive direction. So there you go. We just did a Newton's second law problem with rotation. Okay. So, yeah, so the units get messy here. Here's okay, what's kind of interesting about this is that we ended up with, if you went strictly here, there are no radians, right? You can't really see any radians here, but I did write radians per second squared. And so I know we're doing everything in radians, so I decided I should just go ahead and put radians, even though there were no radians over here. And this is an okay thing to do. Remember, radians can vanish, and by the same token, I can put in radians as long as, you know, I know what I'm doing. That this requires judgment on your part, right? You can't just, you just have to think, right? Does it make sense? So in this case, yeah, we're doing a rotational acceleration problem. Yeah, it makes sense. It's radians per second squared. All right. So we're done with this part of the notes, and at this point, I would like you to stop and take a look at this. I'm going to put the link in my playlist, and I need you to watch this video. All right. Hi again. Sorry to come back to bother you, but there is something I want you to do. After looking at the videos, I need you to take a look at the Pivot Interactives Lab, Chapter 11A. I'm not going to grade it, but this is a great example of the vector cross product. So he's got an accelerating disk. The force from the rocket engine is going to be, in the first case, it's going to be at, this will be the force, and then I'll use a different color. This will be R, which if you extend it, it's going to have this angle here. And okay, so that's one case. And then what's really interesting, you can go to the next part, and now he's got the rocket engine. It's shooting its flames out this way, so the force is like this, and the radius vector is like that, which if you extend, this is the angle, and it's not 90 degrees anymore. So think about this. Same rocket engine, same disk, everything's pretty much the same, but the angle is different. Which one is going to accelerate more? The first case or the second case? Think about it. All right. So, okay, now I'm leaving you. Bye-bye.